And then came the orbit. 3T Atlas wasn't cutting through our solar system like most interstellar wanderers do, plunging in at a random angle, vanishing as fast as it came. No, this one threaded itself neatly along the same plane that holds all the planets, as if following a path already known. Its movement was smooth, almost rehearsed, its trajectory sweeping past Mars and lining up toward Jupiter. Every astronomer watching agreed on one thing: this was not random. You're watching Lumora, where science meets mystery. Tonight, we journey into the data, the doubts, and the quiet awe surrounding a visitor that refuses to fit any box we've built for it. ESA's new image, captured by the ExoMars Trace Gas Orbiter in October 2025, may look simple, a single dot against a sea of stars, but behind that dot lies the most controversial discovery of the decade. The team behind the observation knew the challenge. Their camera wasn't designed for deep space, but for photographing Mars's rust-red deserts. Yet they pushed it beyond its limits, collecting long 5-second exposures night after night. When they stacked the frames, aligned perfectly to the comet's motion, something uncanny emerged. A bright, dense nucleus surrounded by a thin, sun-facing halo, but no tail, no evidence of outgassing, no dust streaming away. To anyone who has studied comets, this is heresy. The tail is the signature, the fingerprint, the defining mark of a comet's existence. Without it, the rules crumble. What ESA had found seemed to break one of astronomy's oldest laws, that sunlight always pushes dust and gas away from the sun. And yet, 3I Atlas glowed back toward it, like a mirror or a signal. The ExoMars Trace Gas Orbiter was never meant to look beyond Mars. Its cameras were designed to scan the dusty plains and the thin atmosphere, not the void between worlds. But when 3I Atlas appeared on the edge of the Martian sky, the mission team couldn't resist. They repurposed their instruments, aimed them at the faint speck moving across the stars, and began a series of experimental exposures, each one lasting 5 long seconds. For spacecraft photography, that's an eternity. Cosmic rays strike sensors, noise builds up, even the smallest motion blurs everything into streaks. Yet somehow the team pulled it off. They gathered dozens of usable frames, and when they aligned them, correcting for every pixel, every wobble in the spacecraft's attitude, a shape began to emerge. Not a smear, not a streak, but a compact glow. The object was real, stable, and disturbingly sharp. When the data team compared its apparent width to that of nearby stars, they found something strange. 3A's Atlas appeared twice as broad. That subtle difference meant it wasn't just a point of light. It had structure. A condensed core wrapped in a faint envelope, a coma without a tail. They ran every test they could think of. Cosmic ray hits? No. Optical ghosts? None. Calibration errors? Eliminated. The field stars remained crisp and undistorted, but the visitor stood apart. Extended, blurred only at its edges, as though shrouded by something invisible yet controlled. Still, even with such precision, the spacecraft's resolution wasn't high enough to reveal the true nucleus. At 30 million kilometers away, the best the team could say was this: it was compact, unresolved, but undeniably real. And then came the real frustration, the data itself. Not all of it was public. ESA released a clean stacked image for the world to see, but the raw frames, the calibration files, the dark and flat fields, those remained locked behind team protocols. Researchers outside the mission filed formal requests, even freedom of information petitions, to see the unprocessed data. But weeks turned into months, and nothing came. All we had was that single haunting image, a brilliant point with a faint glow facing the sun, a comet that defied its own definition. This was not how comets behaved. This was how questions began. Every comet we've ever observed obeys a simple truth. The tail always points away from the sun. It's not artistic symmetry, it's physics. The radiant energy of sunlight, combined with the steady flow of charged particles known as the solar wind, pushes gas and dust outward. That pressure sculpts every comet's appearance, forcing its tail to trail behind like a windsock caught in a storm. Imagine spraying water from a hose into a strong fan. No matter which direction you point the nozzle, the spray bends away from the wind. Comets behave the same way. Their dust tails, pale, wide, and graceful, curve gently outward, while their ion tails, thin and bluish, slice straight along the line of solar wind. It's one of the most predictable patterns in the universe. Even when a comet rounds the sun and reverses its orbit, the tail flips instantly, always keeping its back to the light. For centuries, this has been astronomy's most reliable compass. You could look at a comet's tail and tell exactly where the sun was, even if it was below the horizon. But 3i Atlas refuses to play by those rules. Its glow doesn't stretch away from the sun, it points toward it, a faint halo directed at the very source that should be blowing it apart. This isn't just a visual oddity, it's a violation of the fundamental physics that defines comets themselves. For such a reversal to occur, the forces at play must be completely different. Either the material surrounding 3i Atlas is responding to something other than solar radiation, or the object itself is somehow controlling the emission of its light. Some scientists suggested that maybe we're witnessing an illusion, an angle trick caused by perspective. But even when adjusting for orbital geometry and spacecraft positioning, the direction still doesn't add up. The glow remains sunward, persistent, precise. That's why researchers around the world took notice. A comet that breaks the rule of sunlight is more than a curiosity. It's a message written in defiance of the universe's oldest laws. And the deeper they looked, the stranger it became. Because 3i Atlas wasn't just pointing at the sun, it was aiming. When astronomers first mapped the orbit of 3i Atlas, they expected a wild, plunging arc, the kind of chaotic trajectory typical for visitors from interstellar space. But the data said otherwise. Instead of slicing through the solar system from some random angle, 3i Atlas entered almost perfectly along the ecliptic plane, the thin, flat sheet where every major planet orbits the sun. That might sound trivial, but it's anything but. The odds of a random interstellar object aligning itself with this plane are less than 1 in 100, and that's before considering what came next. After its entry, 3i Atlas didn't just drift aimlessly. It passed close to Mars, slowed slightly, and then, weeks later, approached Jupiter. To orbital engineers, that sequence looked familiar. A textbook gravity assist, the same maneuver spacecraft used to steal a planet's momentum and slingshot deeper into space. Nature can create coincidences, but this looked coordinated. Simulations run by multiple research teams showed how incredibly rare such a chain of events would be if left to chance. Billions of modeled interstellar trajectories produced almost none that mimicked 3i Atlas's smooth threading through the planetary system. Some called it a cosmic fluke. Others whispered the unthinkable, that it might be intentional navigation. Previous interstellar visitors like Oumuamua in 2017 and Borisov in 2019 never behaved this way. They cut steep paths, darted in and out, barely interacting with anything. 3i Atlas, by contrast, seemed to choose its encounters, bending its route just enough to dance between two massive worlds. Its velocity, roughly 130,000 miles per hour, ensures it will never be captured by the sun's gravity. Yet its path follows the very structure of our solar system, as if respecting the lanes of planetary motion. It's like watching a probe follow a preset flight plan, one astrodynamicist remarked, and that's where the unease began. If it's natural, it's rewriting orbital probability. If it's not, it's rewriting something far greater. Somewhere between Mars and Jupiter, this glowing intruder seemed to perform a maneuver no comet should ever attempt. Next, the mystery deepens, because when scientists examined 3i Atlas's chemical signature, they found something even harder to explain. When the first spectral data from 3i Atlas arrived, scientists expected the usual comet recipe: ice, dust, iron, carbon, maybe a little nickel. Instead, the results came back upside down. The nickel lines in the spectrum were bright, sharp, and unmistakable, while iron, its usual twin, was missing entirely. Not faint, not hidden, gone. In every comet ever studied, iron outshines nickel by orders of magnitude. That's how we know what they're made of. Remnants of the same cosmic ingredients that built planets and asteroids. But 3i Atlas broke that rule. Its composition didn't fit any known formation model. Some argued the nickel might be trapped in exotic metal-organic compounds, or that iron was locked inside grains too large to vaporize. But others saw something else, a fingerprint of non-natural chemistry, the kind you'd expect from refined material, or engineered alloys. Then came the carbon dioxide readings. Using the James Webb Space Telescope's near-infrared instruments, researchers detected both CO2 and H2O ice, but in a ratio that made no sense, almost double what's found in typical comets. In our solar system, water always dominates. Here, carbon dioxide was nearly keeping up, suggesting 3I Atlas formed in a region far colder and richer in volatile compounds than any we've observed. The anomalies kept multiplying. Polarimetric studies, which measure how light scatters off dust, showed a polarization minimum deeper than almost any comet on record, minus 2.7%. To match that number, the Comet's dust would have to be extremely porous, made of dark, fluffy magnesium silicate grains mixed with ice. That structure would make it both darker and more reflective, paradoxically efficient at controlling how it shines. In simpler terms, it wasn't just reflecting sunlight, it was managing it. Even its size defied expectation. Thermal modeling based on data from Hubble and JWST placed its nucleus at least 3 miles wide, a behemoth among interstellar visitors. Most objects that large would have been shattered long ago by cosmic radiation and micrometeorite impacts. Yet 3I Atlas remained intact, pristine, and unscarred, as though built to endure. Piece by piece, the puzzle refused to fit. No tail, a sunward glow, a deliberate orbit, a chemical signature that flipped nature's logic on its head. If this was a comet, it was a kind we'd never seen before. If it wasn't, then what exactly was moving between Mars and Jupiter, shining back at the sun? As October 2025 faded into November, one final piece of the puzzle was supposed to arrive: high-resolution images from NASA's HiRISE camera aboard the Mars Reconnaissance Orbiter. The timing was perfect. 3I Atlas would pass close enough to be captured in remarkable detail. But the universe has a sense of irony. Just as the window opened, a U.S. government shutdown froze operations. Data processing halted, transmission queues stalled, and the world waited for images that never came. Days turned to weeks. Forums erupted with speculation. Had the images revealed something beyond explanation, or was it simply bureaucracy slowing down science again? Without official updates, rumor filled the silence. Alleged insider leaks claimed the object showed geometric shadows, structured reflections, hints of design. Others dismissed it as internet fantasy. But the longer the agency stayed quiet, the more the mystery grew. Inside the scientific community, frustration boiled over. Researchers demanded transparency. They wanted the raw frames, the calibration data, the context, anything to separate reality from rumor. Because without it, the line between evidence and belief began to blur. Even the experts couldn't agree. Harvard astrophysicist Avi Loeb, never shy about questioning convention, suggested that when multiple independent anomalies align, a directed glow, an intentional-looking orbit, chemistry that defies origin, the possibility of artificiality should at least remain open. Not as proof, but as a hypothesis that deserves testing. Others pushed back, warning that excitement can distort objectivity. Extraordinary claims, they reminded the public, demand extraordinary evidence. And yet evidence was exactly what no one could fully access. In Vienna, the United Nations Committee on the Peaceful Uses of Outer Space quietly debated a new emergency framework, one that would compel instant data sharing whenever another interstellar object is found. For now, it remains only a draft, a reflection of how unprepared humanity still is for a visitor that doesn't fit the script. As of today, 3I Atlas remains unresolved. The high-resolution data are still sealed behind administrative doors. Its strange chemistry, its impossible orbit, and its mirrored light remain unverified puzzles suspended between science and silence. But one truth endures. Whatever 3I Atlas is, it's forcing us to confront how little we truly know about the space between the stars. This is Lumora, where science meets mystery. And somewhere, beyond the orbit of Jupiter, a light still burns, aimed not away from the sun but straight toward it.